C, your center of mass for the rigid body, and you have the resultant force with the center of mass. What is the fundamental difference between a rigid body and a particle?
The moment angular.
Okay, and
They have 6 degrees.
there are additional degrees of freedom, in particular the rotational degrees of freedom. Okay, there is the rotational contribution of that, which means that it's not only subject to forces, but also subject to moments. So this is the moment, not I. I is the number of the body. So we're analyzing a single body. Okay? So in our analytical mechanics, maybe the first useful one was the principle of virtual power analyzing dynamics, which is, by the way, the principle of virtual power includes 2 main principles. What are these?
Virtual work and
Principle of virtual work
addition also.
and
D'Alembert.
D'Alembert's. Principle of virtual work applies only to static equilibrium. To extend it to dynamics, then you have to add the inertial force. And the principle that allows you to do that is D'Alembert's principle. This was principle of virtual power from J equals 1 to large n, I equals 1 to large n, number of particles or rigid bodies. And we have Fi minus Mi Ri double dot, dotted with the useful part of the equation of motion. So this is partial Ri dot, partial Qj dot, right? This should equal 0. First of all, for a rigid body, we will need to specify what point. So here we will specify that it's the center of mass, right? The center of mass. And this takes into account the translational version. So I need to add a term for the rotational version. Any suggestion how it should look like? Replace the force with the moment. Replace the d by dt for linear momentum by
Angular momentum. HC.
d by dt for angular momentum, so minus hci dot,
Inertia.
dotted with the velocity coefficient, partial linear velocity, so it will be partial angular velocity, partial Qj dot. This is 0. Okay? So now this is the principle of virtual power for when accounting for a rigid body. So this I is a counter over all particles and rigid body. If it's a particle, you don't have the green part. If it's a rigid body, you have both parts. And this J runs from what to what? J?
Generalized.
1 to little n, your whole number of degrees of freedom, all number of q's, little q's, right? That's fine, the principle of visual power is useful, but we got used to Lagrangian's equation, and this is really much easier, so let's see what changes, okay? Here's the Lagrangian equation, d by dt, partial L partial Qj dots, minus partial L partial Qj equals your non-conservative plus your constraint, which is summation k to m ak or lambda k akg. Okay? This part is for the constraint. It has nothing to do with particle or rigid body. Right? We got this term from the constraint equation, so it's exactly the same. It doesn't change. So let's see these terms. These terms are just two scalar functions. the Lagrangian and the work function, right? The Lagrangian for sure it's exactly the same. It's T minus V. What about T and what about V? V is easy, the potential energy is easy. Because the potential energy depends on the forces. So the only force that we can talk about maybe for the differentiate a particle or the rigid body is the gravity. It's mg here and mg there. And when you get the potential, it's mg h, right? But what h now? If it's for the particle, it's the height of the particle above your datum.
Center of mass.
Exactly. If it's a rigid body of several points, intuitively you're gonna select the center of mass. So that's okay. So now we are concerned with two quantities, T and the Q. How they change. Here is the Q. I'll tell you about the Q. I'll remind you about the Q for the particle. It was like this. I equals 1 to n, and we did an awesome quiz on that. It's your non-conservative force dotted with the velocity coefficient, as easy as this. It's this part actually, the force dotted with the guy. The conservative force is already taken care of in the potential, and if you have a non-conservative, it's still in the equation, you need to account for it separately. So this was for the particle. Do you suggest how to modify it for a rigid body?
Moments.
Yeah, just add this term as well. So this is plus the moment non-conservative. So non-conservative I dotted with partial omega I partial QG. So add one more term, the green term. Okay? Add the green term. Moment dotted with the velocity coefficient, but now we're talking about angular velocity. So we need this, okay? Because it's a rigid body. And of course, you're going to have problems about rigid bodies. So you can now go and re-solve the number 4, homework 2. And you know how to account for forces and moments, non-conservative, for rigid bodies. Any question about that? So the only thing remaining here is what? Only thing remaining here is what?
Potential.
Kinetic energy. So here is the Lagrangian equation, the black one. This guy is exactly the same. This guy, we added one term. L is T minus V. V is just a little change. And we're just concerned with T now. Is it the same T or not? So let's do that. Any question?
The first equation, it governs the Newtonian mechanics, that this is how we are going to apply it to the rigid bodies.
Yes, but it's not quite exactly the same as Newtonian mechanics. Because these are the applied forces and moments only. You typically ignore the constrained forces. You don't do that in Newtonian mechanics. So let's just plot this here in a more clear one. This is partial omega I, partial Q, A dot. Okay. And here is your rigid body. So this is the center of mass. This is your R center of mass. This is some D mass with its position vector R, and the distance between these guys is little r. Okay? I want my kinetic energy, please. The kinetic energy is what? Can you tell me what's the kinetic energy? Well, I distributed my rigid body into an infinite number of particles. And indeed, I know the kinetic energy of the particle. What's the kinetic energy of the particle? What's the kinetic energy of the particle?
The resultant RC.
1/2 m. Now just to call dm, my particle.
RC dot square.
Let's see, r of the particle. Dot squared, I'm going to integrate, right? And what is this R dot? From this triangle, it's simply RC plus little r. So the same R dot, little RC dot plus little r dot, all squared, so gives you 3 terms, right? The first term is 1/2 RC dot squared integration of dm. The second term is, you have 2, get away with the 1/2 RC dot dotted with little r dot dm. Plus the third term, 1/2 little r dot squared dm. Any question about that? RC is the position vector of the point C. Has nothing to do with the whole body. You can always get it outside of the integration sign. I'm integrating over all the body, but this is for a particular point. When it comes with little r varies with the particle, so I have to keep it inside the integration sign. So what's the whole integral of dm? What's that? What's that? The total mass of the rigid body. So the first term is very easy. The first term is 1/2 total mass times Vc squared, right? 1/2 mv squared and velocity of the center of mass of the rigid body. This is very expected. And the intuition might say from the beginning that this is the kinetic energy of the rigid body. Or if you have a problem right now, I want to solve it without today's lecture, using Lagrangian mechanics, you're going to do it like this. T is 1/2 mv squared. But there are additional terms. Let's get these. This dot, I will just have the d by dt outside of the integration sign, okay? And what do you think about the integration of little r dm? What's that?
0.
This is 0. We discussed it several times before. So we end with this term. So I have to add this term. Plus 1/2 little r dot squared dm. Just remind me of what is r dot. Anybody remembers? Anybody remembers that r dot? You have a midterm next week. It's omega cross r because it's just due to rotation. It's a rigid body, so the distances between points are rigidly connected. They don't change as a magnitude, but they rotate with the rigid body. So the derivative is simply omega cross r, and we do the usual trick that is negative r cross omega, right? And replace the cross product with matrix product. R tilde times omega. Omega is a vector, 3 components, and R tilde is the skew symmetric matrix corresponding with the vector R. Okay? So, do you know what is R dot squared? If you have a vector and square it, how do you do it?
Vector times mag.
Say it again, please.
Vector into its magnitude.
Yeah, it's the vector times itself. So in the matrix language, it's R dot transpose as a row times a column, right? And I will apply this rule here. Each R dot is negative R tilde times omega. So this guy is the transpose of it, the transpose of the blue. When you do the transpose, you reverse the order, right? So you have omega tilde, omega transpose, omega transpose first, and R tilde transpose. What is R tilde transpose? R tilde is a skew symmetric matrix. You remember what do you mean by skew symmetric? So the element Aij is negative the Aj. It's anti-symmetric.
It's the same.
So if you do transpose, you get the negative matrix. So this negative goes away, and you have R tilde. So this is the first term. The second term, which is R dot, I'm just going to get it from here as is. So negative R tilde times omega. And I will substitute this here. So my kinetic energy is 1/2 mvc squared plus 1/2. Omega is for the whole rigid body. It's not for every single point has its own omega, so I can't get it outside of the integration sign. And the objective of this whole trick is to get the omegas out so that I can get it out of the integration sign. One from here and one from there. Now I have integration of r tilde dm. You remember what do we call this black guy? Alright, this is the moment of inertia. So the final expression for the kinetic energy is 1/2 mv squared for the center of mass plus 1/2 omega transpose I omega, and we're done. So you just need to add one more term for the kinetic energy. This is the translational kinetic energy, and this is the rotational kinetic energy. So for a single rotation, omega is not a vector of 3 components, just one omega. So this will be 1/2 I omega squared. So it's pretty close to 1/2 mv squared, right? Just we replace the m by I for rotation and the v by omega for rotation, right? So 1/2 mv squared plus 1/2 I omega squared. But this is the very general version of it, okay? So in summary, rigid body, how to deal with it within the framework of analytical mechanics or Lagrangian mechanics. All what you need to do is add one more term for the kinetic energy and one more term for the non-conservative load. That's it, okay? That's one more term for kinetic energy and for the non-conservative loads. Let's have an example.
Oh, what is the J term again?
J, where is J? So remind me.
Like the green over there, you have L omega transpose. Is that a J or what is the symbol after omega transpose in green?
Omega this thing?
It's bracket.
Yeah.
It's a bracket just to indicate that it's a row. It's a bracket without, it's
Okay.
not a bracket like this, it's a bracket like that.
Oh.
That means it's a row.
This is,
Oh.
just to stress the fact that it's a row.